Okay, now we're going to have a look at the limit of a function regarding infinite limits. Okay, so when a function is going to positive or negative infinity. So you have on your worksheet number 8, and I've kind of mimicked the graph that you have there. So we're going to just look at how we would read these limits. So when we have a graph, it's fairly easy. We do what we did before. So we say, if we're looking at the limit as x approaches negative 3 of this function a of x. So here we are at negative 3. From the left side, on the left side of negative 3, we get closer and closer and closer to negative 3. Our function is shooting up to positive infinity. I was on the left side. On the right side of negative 3, as we get closer and closer and closer to negative 3, our function is shooting up to positive infinity. So they're both going to positive infinity. So the limit as x approaches negative 3 of a of x is equal to positive infinity. Now, sometimes you will find a textbook that will say that the limit doesn't exist. So truly, infinity is not a number we can just go find and put in our calculator or anything like that. But I am on the side of just writing down the fact that we know it's going to positive infinity. Although that's not a number that we can crunch, put in our calculator, whatever. Go ahead and write down infinity so we know where we think it's headed. So I'm in favor of that. The limit as x approaches 2 from the left of a of x. Okay, we're over here at 2, and we're on the left side of 2. On the left side of 2. On the left side of 2, it is going down to negative infinity. All right. How about as the limit as x approaches 2 from the right? Okay, from the right side of 2, it looks like it's going up to positive infinity. That is what it says. Okay. How about the limit as x approaches negative 1? The limit as x approaches negative 1, from the left, it's going to negative infinity. From the right, it's going to negative infinity. It is negative infinity. All right, so these are all indicative of vertical asymptotes. I didn't draw these, but now I will. Okay, let's pretend like this lined up, like I had intended it for it to. At negative 3, at negative 1, at 2. We've seen and we've drawn these kind of lines on different graphs that we've done before so we can see the vertical asymptotes. These are indicative of vertical asymptotes. Here's the definition. The limit as x approaches some number a from the right, or the limit as x approaches some number a from the left of some function. If we approach it from the left and it either goes to positive or negative infinity, then x equals to a is a vertical asymptote. That's all we got to have. You don't have to have it approaching from both ways. Or from the left, if it's going to either positive or negative infinity, we'd say x equals to a is a vertical asymptote. Certainly, if they're both approaching it going the same direction, yes, that's a vertical asymptote. But you only have to have a one-sided limit to call out a vertical asymptote. So for instance, let's just say that this part of the graph did not exist. The limit as x approaches negative 3 from the right is going to positive infinity. That is enough for me to say x equals to negative 3 is a vertical asymptote. Either one-sided limit going to infinity counts as a vertical asymptote. So E says write the equations. Equations of vertical lines are x equals. Equations of vertical asymptotes are x equals. So right here, x equals negative 3 is a vertical asymptote. At negative 2, oh, did I put that at negative 1? Dang it. Okay, pretend like that's a negative 2. Sorry. Okay, the limit as x approaches, oh no, that was right. Sorry. That was right. The limit as x approaches 2 goes to infinity. Either one of these would be enough for us to write this statement. X equals to 2 is a vertical asymptote. X is 2, and right here, x is negative 1 is a vertical asymptote. So that's what you can talk about for number 8. Now, next, what if we don't have a graph at all? So up to this point, we've looked at it graphically, which it's pretty easy when you have a graph. You can just see exactly what's happening. What if you don't have a graph and they're asking you to find a limit? Look at all these. We even have trig functions. We have log functions. We have to deal with this. So we ought to think through this. So before we handle this without any kind of graph at all. I need to just talk about the concept of division by zero. We know division by zero is not allowed, but we know that if you're dividing by something that's not zero, but it's very close to zero, that is allowed. So let's look at what happens here. What if I have the number 1, and let's divide it by the number 1. Okay. This is a fraction, and it means divided, right? This reads 1 divided by 1. What if we have 1 divided by 0.5? What if we have 1 divided by 0.1? What if we have 1 divided by 0.01? 1 divided by something smaller than 1 is 0.5. Or if I could say that, I could call that 1/2 if I wanted to. 0.1 would be 1/10 or 0.1. What if I say 1 divided by something smaller, 1/100. 1 divided by something smaller. I'm going to go back to writing in decimals so you could see you could do it either way. 0.0001. 1 divided by, sorry, 0.001, that's 1/1000. 0.0001. 0.00001. These are, relatively speaking, these are small, but not very small. Something really small would be like 1 times 10 to the negative 20th, 0.0001, something like that. So we can get very, very tiny, but let's just see what's happening. Let's pick up on a pattern. 1 divided by 1 is the number 1. Okay. 1 divided by 2 is the number 1 divided by 1/2 is a 2. You could do keep, change, flip to prove this to yourself. 1 divided by something smaller than 2, 1/10 is going to be some 10. 1 divided by 1/100, or 0.01, or 001, is that, let me see, what is 100? That's 0.1. This is 0.01. Would be 100. 1 divided by 0.001 is 1,000. This would be 10,000. This would be 100,000. Okay, what do we see? What can we pick up on? Well, when you take a number and you divide it by something smaller and smaller and smaller and smaller and smaller and smaller, the result gets bigger and bigger and bigger and bigger and bigger and bigger and bigger. So let's imagine that we were dividing a number by something very tiny. Something very tiny. This would make it really, really, really big. Something big like infinity. That is what would happen. So very tiny means something very close to zero. Close to zero. Okay, but not zero, but close to zero. So also let's just remember this rule. A positive divided by a positive is a positive. A negative divided by a negative is a positive, or a positive divided by a negative, negative divided by a positive gives us a negative. Let's just remember those rules. Now, we're ready to approach this. Okay, ready? The limit as x approaches 5 from the left of this. So, if we just put in straight 5, what would happen? 5 plus 1 is 6, okay? But 5 minus 5 is 0. We can't divide by 0. But they're not asking us to put in 5. They're saying a little bit less than 5. 5 from the left would be something like 4.999. But just so we can see what's happening, put in something a lot smaller than 5 so we can see what's happening. What if we put in something like 4.9? Imagine this said 4.9. Well, okay. If we put in x is 5, 5 plus 1 is a positive number 6. 4.9 minus 5 would be a negative number. So 4.99999, something really close to 5 from the left, minus 5 would be something very tiny, close to 0, and negative. Okay, so what we have is a positive number divided by something very tiny, close to 0, and negative. A positive divided by a negative is a negative. This is going to go to negative infinity because we have a number being divided by something very tiny. Right here, what's happening here? The limit as x goes to 3 from the left. Okay, so if we're a little bit smaller than 3, so you can imagine something that's pretty far away from 3, relatively speaking, something like 2.9, what would happen? 2.9 minus 3 would be negative. And a negative raised to an odd power would be a negative. So something very tiny and negative is what you get in the denominator down here. Something close to 0. And then, but this would be something like square root of 3, square root of 2.999. Okay, this gives us the square root of something positive is a positive over something tiny and negative. This is going to go to negative infinity. That's what's going to happen there. All right, the limit as x approaches 0 from the right of the natural log of sine of x. So we have to remember some trick here. Okay, here is our unit circle. And the y values on the unit circle are the sign. So when x is 0, right, let's see, this is 0. The sign of 0 is 0. All right, so that's true. Okay. So the sign of something a little bit bigger than 0. So here's a little bit bigger than 0 right here. Right? So this is important for us to remember. If the angle value is a little bit bigger than 0, then it's on this side of the x-axis, which means that the sign is positive. So we're looking at something positive, but it's close to 0, but it's not quite 0. So this is what it's going to be, close to 0, something very small and positive is what positive. Small and positive is what the sign of x is going to be. That it's not just that, we're taking the natural log of something small and positive. So remember your log graph? This is what a log looks like. It has a vertical asymptote here, and then it starts to increase here. So if we're taking the log, the natural log, or any log with a positive base of something very small but positive, we're on this part of the graph. We're way down here. So this is telling me that the log of the sine of x when we're taking it at 0, close to 0, is going to be something small and positive. The natural log of something very small and positive is going down at this point to negative infinity. That's how you have to think through that one. All right, let's look at the cotangent of x. Cotangent, if you remember your trig functions, is defined to be the cosine over sine of x, right? So if you remember your unit circle, hopefully you remember something about trig. Let's see. The cotangent of x is the cosine over the sine of x. Okay, so basically they're saying look at the limit as x approaches pi from the left. Okay, so I am a unit circle person, so I always think in these terms. Here is pi. So something a little bit less than pi, remember, angles get bigger as we go in a counterclockwise direction. So something a little bit less than pi is going to be on that side of the x-axis. So if we're looking at the cosine of pi, a little bit less than pi, it would be 0 if it was at pi, but it's not quite there. So it's a little bit tiny. It's tiny and negative. No, sorry. Cosine is -1, I'm sorry. The cosine would be close to -1. Not exactly -1, but close to -1. But what would the sine be? Okay, the sine is up here, so it's positive, right? Because it's still up above the x-axis, so it's positive, but it's almost 0. It's tiny and positive, close to 0. Something being divided by something that's 0 is going to go to an infinity. A positive divided by a negative or vice versa gives us negative infinity. So that's going to be negative infinity. Okay, down here, let's have a look at this. The limit as x approaches 2 from the left. Let's think about this one. This is a rational function. You learned about vertical asymptotes and holes, hopefully. You can factor this function. Let's factor out an x. This is the limit as x approaches 2 from the left of this. We could say this is x times x minus 2 over, this will factor into x minus 2 times x minus 2. Okay, let's just look at this. What if we put in 2? What would we get here? We would get We put in 2, a little bit less than 2, so something a little bit smaller than 2, what will you get? Let's just look at this. Let me do it this way. If we put in something a little bit less than 2, we would get, this would be close to 4 minus 4, right? And if we put in something a little bit less than 2, we'll get 4 minus negative 4 times 2 is 8 plus 4. We're going to get a 0 over a 0. Okay, so we're going to see what we're going to be doing pretty soon. I'm going to go back and factor this real quick because you know about rational functions. Let's just think through this. This is factor out of x. You have x minus 2. Factor this into x minus 2 times x minus 2. We know from our knowledge of rational functions that if these cancel, we actually just have a whole at x equals to 2. That's what would happen there. Okay, so you're allowed to work with this reduced function. Let's imagine this. What if we have something a little bit less than 2? A little bit less than 2 would still be something positive, right? And something a little bit less than 2, let's put something like 1.9 in here. 1.9 minus 2 is going to be a negative 0.1. So 1.999 closer to 2 minus 2 is going to be tiny and negative. And so this would yield negative infinity. Did every one of these give us negative infinity? I guess so. You can have instances where you get a positive infinity. These just all happen to be negative. So that's how you can think through these limits when you have a when you are not given a graph. Okay.